Hi guys, here's the review for the S2 Chapter 1, 2 and 3 review test. It's all about approximations, binomials, Poissons and normals and all that good fun stuff. So, question 1. During morning hours, employees arrive randomly at an office drinks dispenser at the rate of 2 every 10 minutes. As soon as you see that and you see a value every certain number of minutes, you're looking at a time frame. Now, when you're looking at a time frame, you know we're leading into a Poisson. Well, 9 times out of 10, we're going to be leading into a Poisson. It says the number of employees arriving at the drink dispenser is assumed to follow a Poisson distribution. So there we go. They've already told us. So, part 1. Find the probability that fewer than 5 employees arrive at the drink dispenser during a 10-minute period one morning. Note the 10-minute period has been maintained. 10, 10. That hasn't changed. That's useful for us. Okay? So let's define our distribution. X could be equal to the number of employees that are at this drink dispenser. Okay, at drink dispenser in 10 minutes. Okay, so it's got to be a 10-minute interval because they've defined the interval there. So let's go for our distribution then. We've already been told that it can be modeled using a Poisson. Poisson with a mean of lambda, but they've told us that it's a rate of 2 every 10 minutes. So if we're dealing with 10 minutes, it's Poisson distributed with lambda equals 2. So part 1 says find the probability that fewer than 5 arrive there. So we're looking at the probability that x is less than 5. Okay, but remember that with these discrete distributions, we don't leave it as a less than or a greater than. We change it so that it's got an or equal to. Because remember that our calculators can only deal with the less than or equal to cases for binomial or Poisson. So we change this to be x is less than or equal to 4. This is where we go to our calculator. We need to be in the right mode, so we click menu. We go down to 7, which is the distribution function. Now we needed the Poisson, so go down a page. We're left to the Poisson dA because we're looking at a or greater than, less than or equal to, not a or equal to case, just a or equal to for DP. For the dA, we want the inequalities. We'll do it for the variables, and we're going to say that x is equal to 4 and lambda is equal to 2. Okay, so plugging that equal there, we've got our value of the probability being 0.947346981, which is also equal to 0.9473 to 4 significant figures. As a general rule, although they accept 3 significant figures, I often give distributions to 4 significant figures, just because if you look at tables, that's how they're normally given. So 0.9473 would work for that one. Okay? Part 2. During a 30-minute period one morning, the probability that n employees arrive at the drinks dispenser is the same as the probability that n plus 1 employees arrive at the drinks dispenser. Find the value of n. So you need to be very careful here. First of all, they've changed the distribution because they've said in a 30-minute period. So we've got a new distribution now, which I'm going to call y. So y could be the number of employees at the dispenser in 30 minutes. Now we originally had in 10 minutes, so we've got 3 times a greater period now. So if our time frame is now 3 times as great, that means that our rate should be 3 times as great. The rate was originally Poisson distributed with 2, but if it's now 3 times greater, 2 times 3, it's now Poisson distributed with 6. Now remember your formulae for this. If you're unsure about the formula, I'm just going to show it very quickly on the screen. Oh, that's not what I wanted. I wanted this one. Okay, here's your formulae for stats 2, formulae page. Be aware of the fact that we're dealing with a Poisson. This is the probability that x is equal to x. Now, because you've not been given a value for x, you're actually going to have to use this for this question. So the probability that x is equal to some value is equal to the exponential to the power of minus lambda multiplied by lambda to the power of x divided by x factorial. Okay, so let's get back to this then. Our calculator as well. Okay, so making a note of that, for later on if you wish. You can have the formula written up here. The probability that x is equal to x in a Poisson is the same as e to the minus lambda multiplied by lambda to the x over x factorial. That's what we're going to do here, because we're talking about the probability that n employees arrive at the drink dispenser. So first of all, I could work out the probability that y is equal to n. Well, that's the same as saying e to the minus lambda multiplied by lambda to the power of n, because x is n in this case, all divided by n factorial. Okay, so I've got my first one. It says it's also the same as the probability that n plus 1 employees arrive at the drinks dispenser. Well, the probability that y is equal to n plus 1 is equal to e to the minus lambda multiplied by lambda, this time to the n plus 1, over n plus 1 factorial. Okay? So, different now, because we've got two things in terms of lambda, n, and e. Okay? But our lambda, we know what it is. Our lambda was equal to 6. So I can replace that e to the minus lambda to be with 6, and that lambda there to be 6 as well. And the same here. That lambda can become minus 6, and this can become 6. Things become a little bit easier at this stage. Now, the fact they're equal to each other means we're going to have to actually set them equal to each other. So I'm going to have e to the minus 6 of 6 to the power of n over n factorial is the same as e to the minus 6 multiplied by 6 to the n minus 1 over n minus 1 factorial. Okay, things I can do straight away here. Things I can cancel. I can cancel my e to the minus 6 from both sides. That can go, because they're the same, it's a constant. So what I'm actually left with now is 6 to the n over n factorial is equal to 6 to the n minus 1 over n minus 1 factorial. Now, it makes sense at this stage to get any 6 to the n's, or 6 to the n minus 1, basically powers of 6 on one side, and the factorials on one side too. So what I'm going to do is I'm going to multiply both sides by n plus 1, n minus 1 factorial. Except that is n plus 1 factorial, so I don't know why I've started writing n minus 1. It was n plus 1, n plus 1. I'm going to multiply both sides by n plus 1 factorial. Up here, I'm going to have n plus 1 factorial. And I'm going to divide both sides by the 6 to the n. So what I'm going to do, I'm going to rearrange my fractions. So I've got n plus 1 factorial over n factorial on the left. And dividing both sides by that 6 to the power of n, I'm going to have my 6 to the n minus 1 over 6 to the n. And again, that's 6 plus 1. Why have I written minus 1? Very strange. I don't know why I've done that. Let's correct that. 6 plus 1. 6 plus 1. Okay? Easy mistake to make. Now we can think about what each of these actually become. Now this involves a little bit of pure maths thinking. Remember that factorial, n factorial, is the same as n multiplied by n minus 1 times by n minus 2 times by n minus 3 times by dot dot dot, all down to 2 times 1, 3 times 2 times 1. So we're down all the numbers from the value of n down to when n is equal to 1. Okay? Now, by the same logic, n plus 1 factorial is n plus 1 multiplied by n plus 1 minus 1, or n, times by n minus 1, times by n minus 2, all the way down to times 3 times 2 times 1. Now, think about if I'm dividing these through. What am I actually going to be left with? Well, the n's will cancel. The n minus 1s will cancel. The n minus 2s will cancel. The n minus 3s, all the way down to the 2s and the 1s. All I'm going to be left with when I divide is n plus 1. That's all that's going to be left on the numerator of my fraction. Everything else is going to go. Okay? So on the left-hand side, I'm going to have n plus 1. On the right-hand side, I've got to deal with these powers. Now, 6 to the n plus 1, if you think about your power laws, that's the same as 6 to the n multiplied by 6 to the 1, because if you multiply powers together, you add them. But 6 to the power of 1 is just 6. So what I've actually got is 6 loads of n. If I divide 6 loads of 6 to the n, if I divide 6 loads of 6 to the n by 6 to the n, the 6 to the n's will cancel. So therefore, what I'm going to left on the right-hand side is just 6, because those n's will cancel. That means for us, all I need to do now is take away 1. 6 minus 1, So I've now got the value of n for part B. Okay. Okay. So we found the value of n. We found the value of the case where the probability that n employees arrive is the probability the same as n plus 1 employees arriving. So the probability that 5 employees arrive is the same probability that 6 employees arrive in a half-an-hour period. Okay. Last of all, during a 45-minute period, they've changed the time period again, which means the probability change again. So I'm going to have maybe z this time, not to be confused with the z values of the normal distribution. So the z values could be the number of employees at the at the dispenser in a 45-minute period. Okay, well this time, if I think about the Poisson distribution, remember in the right back at the beginning, that when it was a 10-minute period, there were 2 of them. So what I need to do is I need to multiply that 10 minutes by 4.5 to make it 45 minutes. So I need to do 2 times 4.5. 2 times 4.5 is 9. So this new distribution is Poisson distributed with 9. So it says the probability that between C and 12 inclusive employees arrives at the drink dispenser is 0.546. And arrived at C. Well, what they're looking at here is the probability that we are between C, and it says inclusive. Inclusive means it's or equal to. So C less than or equal to our value Z, less than or equal to 12, is equal to 0.8546. When you get to this stage, what we need to do is we need to consider what that actually means. And remember, we can only deal with probabilities in our calculator, for example, of Z being less than or equal to a value. Okay, that's the only way we can actually deal with these. We don't like it in any other form. So think about it this way. If I could rewrite this, I could say this is the same as the probability that Z is less than or equal to 12, but then I'd need to take away a little bit, because effectively this gives me from 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1. It gives me all of them. But I don't want all of them. Let's say, for example, that C is equal to 5, for example. Then that means that from 5 downwards, I don't want it. I'd need to take away the probability that Z was less than or equal to 4. I'd need to get rid of all these ones. Likewise, let's say that C was equal to 8. Well, because 8's included, I'd be saying, well, I want 8 to be included up here in that value. I'd need to take away the probability that Z was less than or equal to 7, 1 less than 8. The fact that it's C just means that we need to do the probability of Z being less than or equal to C minus 1. 1 less than C. The letter C minus 1. Okay? So that's now equal to 0.8546. Let me rewrite that. Okay. Now, if I look at that, there is one thing I can calculate. The probability that Z is less than or equal to 12. So I'm going to go to my my menu, my distribution function, and I want the Poisson cumulative. So 3, list, X this time is equal to 9, not 9, 12, and lambda is equal to 9, and that gives me a value of 0.7577 34371. So I'm going to type that in there. So I've got there 0.8757734371 minus the Poisson of Z less than or equal to C minus 1 being equal to 0.8546. Well, if I take away both sides now, I would end up with minus P on its own, but I don't want a minus P. So what I'm going to do is I'm going to move that P over here. That would make that P positive. If that P is positive, the probability is positive, I can take away both sides, the 0.8546, meaning the probability that Z is less than or equal to C minus 1 is the same as 0.8757734371 minus 0.8546. Okay, so I've got that saved in my calculator already. So what I'm going to do, I'm going to go to my normal calculator mode. That is my answer, as you can see, and I'm going to take away the values that I need, the 0.8546. Even with 0.0211734371. So now I've got to the stage where I know the probability of Z is less than or equal to C minus 1. That's great, because I'm now only in terms of that C, and I can start to unravel it. And what I need to be very careful of this time is, this is where I need to work backwards. I need to start working my way up the probability distribution. So I need to check different values of Z to see at which point I actually exceed this value for the probability that Z is less than or equal to some value. So starting off with a very basic case, I look at the probability that Z is less than or equal to 0. So just going into my calculator to number 7, to the Poisson cumulative, the variable, assuming that X is going to be 0 to begin with, but lambda is the same, it's 9. I can see that the value I get is 0.001 2 ... That's clearly smaller than the value I've got for here. So making that is less than the probability that Z is less than or equal to C minus 1. I'm looking for the first time I exceed this value. So next I'm going to check the probability that Z is less than or equal to 1. So just go to my calculator, change one thing about it, which is change X into 1, and I get 0.01. That's still smaller than this. So still I'm going to have, that's less than the probability that Z is less than or equal to C minus 1. So I've not reached it yet. Next I'm going to change, I'm going to go up to 2. The probability that Z is less than or equal to 2, that is still below what we need. So that's still less than the probability that Z is less than or equal to C minus 1. Okay, well, let's do the next one. And we just keep going with this until we exceed it. And lo and behold, we have basically exceeded it this time, or have we exceeded it this time? 0.0212. We have exceeded it, which is strange because I wasn't expecting us to do so here. There's something wrong with my calculator. This is not what I got earlier. Let's double check that. X9. I guess it worked. Must be the case. Okay, so when I go to this stage, got the probability that Z is less than or equal to 3. That's saying that the well, you can see this time by what I've got on my calculator, this number, this value here, is greater than this value here. Okay. As a result of that, I can say that this is the first time I exceed it, so the probability that Z is less than or equal to C minus 1. What that means for us is that we could say C minus 1 could be equal to 3. It's the first time that I exceed the value given. Okay? Let's check it there, right. So therefore, if I have my C minus 1 there, that could be equal to 3. C should be equal to 4. I was looking for the first time that I exceed the value required. Because beforehand, I didn't meet the value needed. Okay? But now I do. Okay? All of these values that came before, I didn't meet what was needed. I had a value where the probability less than didn't match up. This time, however, is the first time when it actually exceeds what I need. Okay, therefore it's the closest, and I go for that one. Okay, so C is equal to 4 in this case. Okay, just by setting those two equal to each other. Next bit. Find the probability that exactly 2 employees arrive at the drinks dispenser in exactly 4 of the 6 non-overlapping 10-minute intervals between 10 a.m. and 11 a.m. one morning. Assuming that all these 10-minute intervals are independent, what I could do is I could model this as a binomial. Now, we're back to looking at the 10-minute interval. So we're back to the X being Poisson distributed with 2. Okay? If I work out the probability that X is equal to 2, first of all, so using fancy calculator, menu 7, I'm looking at the DP Poisson, the probability distribution. So I've got 2 there, 2 there. X is going to be equal to 2, and the actual lambda is also 2, so it's 2 and 2. That gives me a value of 0.270. 0.67056665. So, my value there. That's the value that I am going to use for the whole thing. Now, this is the probability that this happens that I get one 10-minute interval whereby there are exactly 2 employees. But I want this to happen exactly 4 out of the 6. What I've actually got is now a binomial distribution. So let's say A is the number. This is a new distribution now. I ran out of letters, so I've gone back to A. This is the number of 10-minute slots where there are exactly 2 people, 2 employees. I know it takes a long time writing out these distributions, but it is worth doing, so it is worth marks. So what I know is that A is binomially distributed. With N, there are 6, it even tells you in the question, there are 6 10-minute intervals, non-overlapping, very important, 6 10-minute intervals between 10 AM and 11 AM, so it's got an N of 6. The probability of it happening in any one of those 10-minute intervals is the answer you've just calculated. So 0.276 ... So 0.27 067 05 665. And we're looking to show when this happens exactly 4 of the 6. So what I'm going to have to do here, probability that A is equal to 4. Well, for this again, I can go back to the calculator. So menu 7 for the distribution, but I'm looking at a binomial and it's an equal to case, so it's a DP. So 4, list. First of all, our X value is 4. Our N value, as we just said, is 6. And this value here, P, is the answer I've just given. So I click answer because I haven't cleared it yet. It's there, 2706. Be very careful though, because what I have noticed is that when the calculator rounds it, and you'll see it here as well, I actually round this to 4 significant figures. I'll get 0.2707. I wouldn't get 06. So the calculator truncates the number, it doesn't round it. So be very careful of that. So if you wanted, you could type it in as 0.2707, just in case it gives you a different answer. Okay, but this will give you the right answer for all intents and purposes. Even if further down it's not correct, your rounded form would vary so slightly that it will be okay. Okay, you'll still get the correct answer for what will be on the mark scheme. So here, the probability is going to be equal to 0.0428 255 4198, or as prepared, sorry, 0.0428, and I'll go 2.83 to 4 significant figures. Okay, so that deals with that one. Okay, so in this one, what we need to do is we need to find the probability exactly 2 were there. So it was a binomial with the distribution that I could work out. Sometimes they give you that as a part A, where you find one probability, and then the next bit is to use that probability as a binomial. Okay. Question 2. A salesman sells insurance to people. Each day he chooses a number of people to contact. The probability that the salesman sells insurance to a person he contacts is 0.05. Got a probability. On Monday he chooses to contact 10 people. Well, we've got some information there. We've got a number of people and we've got a probability. So we're looking at binomial. So let's get our distribution set up. X could be the number of people who buy insurance. Okay, so let's say X is equal to number of people who buy insurance. Okay, and that means that X is going to be binomially distributed with our N. N is 10, and our probability is 0.05. Okay, so I've now got my binomial distribution set up. The question we're given, we've got to find the probability sells to exactly one person. So part I, we're looking at the probability that X is equal to 1. Well, on my calculator, menu 7, I am looking at the DP of the binomial. I'm looking at an explicit value, so it's the probability distribution. So for my variable list, I'm looking at X being equal to 1, at N being equal to 10, and at my probability being 0.05. So when I type all them in and I click equals, I get the value of 0.315 124 7049 or 0.3151 to 4 significant figures. So there we go. There's a probability that x is equal to 1. The second question asked you the probability that at least 3 people. Now, at least includes. So this is the probability that x is greater than or equal to 3. So it's the same again, except this time we're not using the DP. We're going to use the next one, the DA, the cumulative distribution function. So hit 1, variable. Most of the information is the same, except that we're looking here at 3. It's been saved before, except I've got that wrong. Apologies. That's greater than or equal to. We want less than or equal to. So I'm going to make that 1 minus the probability x is less than or equal to 2. Remember that we can't do a greater than case on the calculator. We have to change it to a less than. Okay, and when that's or equal to 3, then I can't include the 3. I need to go 1 down because of the discreteness of our distribution. So we're doing actually from 2 with the same information. So 2, n is still 10, p is still 0.05, and our value is this. So what I actually get is 1 minus 0.9884 964426. So I'm going to do 1 minus that value. Well, I'm going to first of all go to menu 1 to do that. 1 minus answer, and I get my value of 0.01150355741. Okay, and we're going to round it to finish off actually. So extend page. Come on, no, I don't want that bit. Go away. There we go. Now I can extend the page. Our value becomes to 4 significant figures 0.01150. Okay, 5, and that's now to 4SF. Okay, so that's part A and B out the way. So we've got 3 of the marks available in that question. Question 2. Find the number of people you should contact each day in order to sell insurance on average to 3 people per day. Okay, this is not actually anything to do with distributions or any of the stuff that we generally do in S2. This goes back to GCSE level. We're looking at expected frequency. Well, what we should know for expected frequency is that if I know the probability of an event happening, and I know how many times I'm going to do an event or something in order to trial this out, if I multiply the 2 together, the number of trials I'm going to have and the probability of a certain event, that will tell me how many events I would expect. So just as an example, as an aside there, if I know that I am going to roll a die, and I know that it's a probability that I get a 5, for example, as a 6th, that's I know that the probability is a 6th. Let's say I want to get a certain number of 5s. I could say, well, if I roll the dice, something like 120 times, I could do a 6 times 20, okay, which is a fairly straightforward calculation, gives us 20. I'd say I'd expect 20 5s because that's the expected frequency. If the probability were a quarter, let's say I was spinning a spinner 120 times, well, I'd be expecting something to happen 30 times. We're doing the exact same thing here. If I call the number of people that he speaks to each day n, then we know that if we want to get the value that he's going to get as 3 people per day buying the insurance, we need to be able to multiply that by the probability that 1 person will buy insurance. And as we know, the probability that someone will buy insurance is 0.05. So 0.05 multiplied by your n should be equal to 3 in order for us to expect the probability to be consistent. In other words, I should divide it. 3 divided by 0.05. 3 divided by 0.05 in our calculator. And we are left with 60. So we should ask 60 people. Okay, hopefully we were able to see the link there rather than it being a bit sneaky and seeing for what it was. Part C. Calculate the least number of people he must choose to contact on Friday so that the probability of selling insurance to at least 1 person on Friday exceeds 0.99. So again, they've added a new distribution here. Now, before we were looking at Monday, and on Monday he chose to contact 10 people. We do not know how many people he's chosen on Friday. He's chosen to contact n people. So let's call it n for now. So I could put down here, y is my new distribution, is the number of people who buy insurance on Friday. We don't know how many. What we do know, though, is that y is binomially distributed still with our n that we don't know. The probability was maintained 0.05. So we now need to think, we're looking at the probability of him selling insurance to at least one person. Okay, the probability that he sells it to at least one person, that means that we're looking at the probability that y is greater than or equal to 1. We want that value to be greater than 0.99. So what we need to do here is we need to start thinking about what that means. Probability of greater than or equal to 1, like before, that's the probability, 1 minus probability that y would be less than or equal to 1 less than 1, which is 0. But we don't do less than or equal to 0. We do just equal to 0. It's the only value you can get. This has got to be greater than 0.99. While dealing with the inequality, what I could do, I'm not going to try and move the p over there. I'm going to keep that p still because I don't want the inequality to get all confused. Take away 1 from both sides. Minus p, or probability of y that is greater than y is equal to 0, is greater than 0.99 minus 1. Well, that's minus 0.01. Now, hopefully remember that to deal with inequalities like that, to make them positive, I have to do something. I can multiply through by the negative, that's fine, but that changes the sign around. So be very careful of that. You've got to make sure that you do swap that sign when you multiply or divide by a negative. That's also going to come in handy later on in this question. So, I've now got this set up. Okay, well, think about this. This y is equal to 0 case, this probability that y is equal to 0 is a fairly easy one to calculate. Because we're actually just looking at, if you think about the binomial distribution, just looking at the values here, you've got here your n choose x, loads of p to the x, loads of 1 minus p to the n minus x. We're looking at the cases when x is equal to 0. Well, n choose 0, no matter what n is 1. P to the power of x, anything to the power of 0, if x is 0, is still 1. So these first two bits are gone. All you're left with is 1 minus p to the power of n minus x. And again, x is 0, so it's 1 minus p to the power of n. It's the case where we only have failures in our binomial model. So what I'm actually looking at is my probability of 1 minus p, well, my p was equal to 0.05, to the power of n being less than 0.01. That's what I'm actually looking at. Or, if 1 minus 0.05 is 0.95. So the n is less than or equal, is less than 0.01. Now, how do you solve these? Well, the way to solve them is to deal with logs. But I must implore you, do not just take the log to the other side. Now, you've done logs in P2. Do not just go to the other side and go, oh yeah, I can just do log to the base of 0.95 of 0.01 and get your answer. Although that will give you the right number, the inequality sounds going to be wrong. What you should do is take logs. So what we're going to do is we're going to have natural log, or log if you prefer, just writing log of 0.95 to the n is greater than log of 0.01. By using the power law, I can move that n to the front. So I could have n of natural log of 0.95 is less than natural log of 0.01. Now, to get n on its own, I need to divide by log of 0.95. So this is what I end up with on the other side. But what you should be aware of is that if I have the log of any decimal, no matter what the log is, log to the base e is what I've taken, but if it was just any general log, log of a decimal less than 1 is a negative number. As you will see if I put it on my calculator, 0.95 is a negative. And remember from earlier on in the question, when I divided or multiplied by -1, the sign changed. So here, I've divided by a negative number. Even if I haven't written as a negative number, it is what it is. It changes the sign. This becomes greater than. So now n is going to be greater than log of 0.01 divided by natural log of 0.95. Now, it doesn't matter if you use natural log or any other log, as long as you maintain the logs. And you're left with 89.78113496. Now, because this is a discrete distribution, the binomial distribution, we know that we can only have integer values of n. So because n must be greater than 89.7, we have to round up. Even if the inequality would have originally been the other way around, for example, we would have still rounded up in this case. Even if the number was not normally one that would round up to 90, because the inequality says that we're greater than, we have to have n is equal to 90 here. Okay, we have to round up because our inequality tells us to do so. Okay, tricky question. Question 3. A company produces nutty choc bars that are made of chocolate and whole hazelnuts. A 40-kilogram batch of the chocolate and hazelnut mixture used to make nutty choc bars will contain 4,750 hazelnuts. Show that the mean number of hazelnuts in an 80-gram bar of nutty choc is 9.5. Well, what I would do here is I would just work out the mean in general. If we know that in a 40-kilogram batch there's this many hazelnuts, work out that mean. So divide the 4,750 by 40,000, since it's 40 kilograms, and that will give you how much you'd expect in 1 gram. For one gram of chocolate, how much hazelnut would you expect? And then just multiply it by 80. So my first step is going to be to do 40, that's right, other way around, 47,550, 4,750 hazelnuts in 40,000 grams of chocolate. Well, that's the same as doing on my calculator. 4750, 12 over 4, 1, 2, 3, 4. And I've got 19 over 160, or 0.1185875. That's how much we expect to see in general. For every gram of chocolate, there is going to be that many hazelnuts. Well, that means that if I've got an 80-gram bar, we're expecting to see 0.11875 multiplied by 80. If I go and times this by 80, I am left with 19 over 2, or 9.5, which is what they wanted. Okay, only a 1-mark question really, but we've got there. The reason that they've given you this value is because you're going to have to use 0.95, and they don't want people to get to this question and go, oh, I can't think of how to do this bit, and then not be able to answer the whole thing. So they're still giving you a chance by making this first bit of proof. Even if it's only worth 1 mark, even if you didn't get it, it's there to use. Now it says here, a Poisson model is suggested for the number of hazelnuts in each 80-gram bar of nutty choc. State 2 assumptions that need to be made for a Poisson distribution to be used, or to be suitable in this case. Now, remember the suitable things for a Poisson. First of all, those hazelnuts, and we need to apply it to the situation, the hazelnuts must occur singularly. Singularly, I think that's how you spell that, I'm not sure. Singularly, okay? Alongside them being occurring singularly, so only one can occur at a time, what also must be the case is that the hazelnuts must be independent of each other. Now, obviously, you guys would have much better handwriting when you write this because you're not writing on a screen with your finger. You would write with pencil and paper, and the examiner would clearly see what you're writing. And then I'm going to write a few more because I'm just giving you a few ideas. We know the other bit is that these must occur at a constant rate. Okay, because that's the other case for the Poisson, is that the rate at which we get must be a constant rate. So hazelnuts must occur at a constant rate. At a constant rate. Whoa. Okay, they must occur singularly, independent of each other, and at a constant rate. Okay, and then you could even, for the Poisson, mention something about the time frame. Okay, you could mention that all these occur over a fixed time frame. However, the assumptions that we're making are not really related to the time frame. They're related to these criteria. Okay. Part C. Find the probability that in an 80-gram bar of nutty choc, that it contains exactly 12 hazelnuts. Okay, first things first, we're going to set up our distribution. So X could be the number of hazelnuts in an 80-gram bar. They've already told you that it's Poisson distributed, so you'd be silly if you start using a binomial. It's Poisson distributed with the mean they also gave you earlier, which is 9.5. Okay, because that was the mean number of hazelnuts in an 80-gram bar, 9.5. So that's the one I'm going to use. That means that what I'm using here for part A, is they want us to find the probability that X contains exactly 12. So X is equal to 12. Well, I go to my calculator, I get menu 7 up, and I'm looking at this case as a DP Poisson because it's an equal. So number 2, my X value is 12, and my lambda value is 9.5. Typing them into my calculator, and I get the probability of 0.08444 009657, or to 4SF 0.08444 to 4SF. 3SF is fine if you do it through 3. Okay. And then the other bit is that it contains fewer than 8 hazelnuts. So II, fewer means explicitly less than, so less than 8. Because it's not or equal to, because fewer means you can't have exactly 8. But changing that into what we need it to be a less than or equal to case. That's the same as less than or equal to 7 in a discrete distribution world. So again, menu 7. This time we're looking at the continuous distribution. Okay, cumulative distribution. So go to 3, list and variable, so variable there. X this time is equal to 7. Lambda is still the same, that's unchanged. And the value that you get is equal to 0.268 which is 0.2687 to 4 significant figures. Okay, so we finished that bit now. That's that bit out the way. I'm going to make that look a bit better. Okay, part D, find the probability that a pack of 3 80-gram bars of nutty choc includes exactly 1 bar with fewer than 8 hazelnuts. Well, we've now moved on to another distribution. We're looking at a binomial here. Let's let Y be the bars with less than 80 grams. Less than 8 hazelnuts. If that's the case, then Y is binomially distributed with, well, we've got a pack of 3. And the probability of this being the case is the one we just worked out. 0.2686631,818. So I've got my probability set up now. This is what I said would happen earlier, that you can sometimes get situations where they give you an earlier part of the question where you're explicitly using a Poisson, and the later part is you use that Poisson to set up a binomial. So what we've now got to do with this is we've got to go and work out the probability that it includes exactly 1 bar with this criteria. So in other words, the probability that Y is equal to 1. So when I consider about my distributions, I'm dealing with the binomial DP, okay? Because I want an equal to case. So I'm looking at my value being equal to 1, my n being equal to 3, and my probability being the answer that I've just got. But again, be careful of the fact that the probability that you put here, again, it has truncated the answer. That 6 has gone to 6 rather than 7. It should still be okay, but if you're conscious, go back and change it to 0.2687 so that it's correct in there. Okay, it's a bit of a failing on the calculator's part. Okay, hitting equals is going to give you 0.431,086,3629. Okay, and then rounding that, I could get 0.4311, so 4SF. Okay, there we go. So that's the probability that we're looking at in this particular one. That's the probability that we're going to have one bar with fewer than 8 hazelnuts out of this criteria. Okay, the last bit. The company also produces a 200-gram bar of nutty choc using the same chocolate and hazelnut mixture. So the fact that it uses the same chocolate and hazelnut mixture means that the mean average of hazelnuts is going to be the same, meaning that we can multiply up our Poissons from earlier. Now the interesting thing is that we before had an 80-gram bar. Now we've got a 200-gram bar. If I think about what I need to multiply 80 by to get 200, let's work it out. 200 over 80. I guess we go to menu 1 for that. 200 divided by 80 is the same as 5 over 2 or 2.5. So in other words, what I've got to do is I've got to multiply my mean from before by 2.5. So let's say for this new situation, again, I've gone beyond y. I don't want to use z, so I'm going to use a. I'm going to say a is equal to the number of hazelnuts in a 200-gram bar. A is going to be Poisson distributed with, go back to what it was originally. Our original case for x in the 80-gram bar was 9.5. I need to do 9.5 multiplied by my scale factor of 2.5. So I'm going to multiply it up and I get 23.75. That's what's going to go in here. That's my Poisson. So I've set up the binomial, I've set up the distribution, but then read the question. It says, use a suitable approximation, that's important, to find the probability that a 200-gram bar of nutty choc contains at least 30 hazelnuts. Well, this value of lambda is big, it's greater than 10. So I might change it to a new probability, a new distribution. I might go for, not the letter B, because the letter B could be binomial. Let's go to D. I don't want to use C. So I could say D is normally distributed, and then the distribution we use when we approximate from a Poisson is lambda, 23.75. Lambda again, lambda. Just as a reminder, because we need to square the square root, so the square root of that squared, just to remind ourselves that we are taking the square root of the standard deviation, or the variance to get the standard deviation when we use it in our formula. Okay. Now the question was, find the probability that a 200-gram bar has at least 30 hazelnuts. We're working out the probability that A is greater than or equal to 30, because it was at least. So when I approximate that, I need to apply the continuity correction. And I'm going to look at the probability that D is going to be, that looks like a P, that D is going to be greater than, because we don't have it or equal to when it comes to the continuous distributions. Look at this carefully. Because it's or equal to, it means we can go on the other side of what it's saying. Now this is normally greater than. If this is saying greater than, then we're expecting it to be, 31, 32, 33. But because it's or equal to, we can go down a little bit. So it becomes 29.5. So the probability that D is greater than 29.5, just use your calculator. So menu 7. We're looking at the DA of the normal, the cumulative distribution of the normal. So number 2. My inferior bit is the lower bit, 29.5. So 29.5. My superior, it's way up. So let's just make it a big number. There we go. Even bigger. Okay. My lambda is the square root of 23.75. I put that square root in to remind me to do that. My mu is 23.75. This now gives me a probability of 0.1190249,463, which is the same as 0.1190 if you want to write it to 4 significant figures. Okay, so there you go. That's your little review test out the way. I apologize if it was quite a long run through, but I hope it's been useful. I imagine I probably would have planned to give half a lesson for this, but it's probably taken the full lesson, in which case I hope it was useful. I hope you had a chance to watch this video. If there are questions, make sure you let me know so that we can go through it again. All right, guys, take care. Bye now.